So, so I'm Diego Mendez. I am from Universidad Javeriana in Bogotá, Colombia. Thank you very much for the invitation. I'll try to present a brief introduction to machine learning and deep learning. This is really challenging because I only have like 60 minutes to cover a lot of material. So don't expect to be an expert after this presentation. This is just going to be a very, very brief introduction. So this is kind of like the outline. We're going to cover the differences between AI, machine learning, and deep learning. Then we're going to talk a little bit about the machine learning paradigm. Then we're going to look at how to find the best solution fitting a model. We'll talk a little bit about regression and classification with neural networks and a little bit of the issues of machine learning training specifically. So this was already part of the questions that we had. So consider the following definitions to understand deep learning versus machine learning versus AI. So artificial intelligence is a technique that enables computer to mimic human intelligence. And machine learning is a subset of artificial intelligence that uses techniques that enable machine to use experience to improve tasks. And deep learning is a subset of machine learning that is based on artificial neural networks. The learning process is deep because the structure of artificial neural networks consists of multiple input, outputs, and hidden layers. Each layer contains units that transform the input data into information that the next layer can use for certain predictive tasks. So thanks to this structure, machine learning can learn through its own data processing. And we will look a little bit of this in more detail later. So what are the general steps for machine learning? So on a high level, machine learning process is comprised of several steps. So of course, the first one is to decide on the question. So most machine learning processes start by asking a question that cannot be answered simply by conditional programming or rules-based engines. So these questions often revolve around predictions based on a collection of data. After that, then you have to collect and prepare the data. To be able to answer your question, you need data. The quality and sometimes the quantity of your data will determine how well you can answer your initial question. Also, visualization is key in these steps. After that, of course, you have to choose a training method. And depending on your question and the nature of your data, you need to choose how you want to train a model to best reflect your data and make an accurate prediction against it. So this is part of your machine learning process that requires a specific expertise and often a considerable amount of experimentation. After that, you train the model. Using your training data, you will use different algorithms to train a model to recognize the patterns in the data. And the model might leverage internal ways that can be adjusted to privilege certain parts of the data over other parts to build a better model. Of course, you have to evaluate your model. Normally, you do this using data that the model hasn't seen before from what you collected before. Of course, there's a step that that is parameter tuning, that based on the performance on your model after being deployed, you can probably redo some parts of the process to fine tune the parameters and then improve the accuracy of the performance of the model. And of course, at the end, you have to use the model and predict. So this is also a part of the question that we had. So consider a typical Internet of Things IoT architecture. Traditionally, the AI techniques, the artificial intelligence techniques are executed under the mighty power of the cloud. So we have the analytics running over here. However, some deployments might not have the necessary bandwidth to transmit all the data to the cloud, or might not have connectivity at all. On the other hand, some specific applications might also have very strict latency requirements that are not met if you have to go to the cloud and back. So the solution is to move these machine learning techniques to the embedded devices, to the edge. Though, of course, there are going to be several challenges in doing that. And not only, and we're going to cover, I mean, this course is not going to be, or this workshop is not going to be just about edge machine learning, but on tiny machine learning. And that's why we say that the future of machine learning is tiny and it is bright. And Marcelo was already sharing some of the slides on how you compare edge machine learning and tiny machine learning, because we're not going to have even a powerful machine like the one you're using to connect to this workshop, but just really tiny devices, embedded devices with really strict computational and memory capabilities. So for many of you, this is going to be just the first encounter with machine learning, and many of the things will be left to be experimented and developed. This is kind of like the workflow we have to follow to collect data, design the model, train it, optimize it, and then deploy it. Of course, we're not going to be able to become experts in 1 week. I just hope you just fall in love with the area and its potential and keep working on your own. So just think about this for the upcoming lectures. So what is the machine learning paradigm? So first, let's talk about explicit coding. So on one hand, we have this explicit coding where we define the specific rules and very clear rules that the program executes. Everything is completely pre-calculated and predetermined, and the scenarios are really, really limited. So in the traditional programming paradigm, we have data and we have rules for the program to calculate answers or to define the outputs. Although for some cases, that might be enough, is not for many other really realistic scenarios. So for example, explicit coding is feasible for simple activity recognition tasks such as walking. You just have a sensor that can measure the speed, and then if the speed is under a certain threshold, you say, okay, the person is walking, or even walking and running. So you just start defining these thresholds on the speed, or even biking. So if the person is biking, of course, the speed is going to be above a certain threshold. But what happens, or if you want to recognize when a person is playing golf? So that seems to be complex to code, right? So let's change this traditional programming paradigm to one where now we provide the data and the corresponding answers, and the machine learning algorithm finds out the rules. It identifies these special data features or patterns intrinsic to the data that allow to generate those answers. So it is now the intelligent algorithm that finds these patterns in the input data to classify the activity of the user. So machine learning techniques can be classified into two main classes: supervised and unsupervised. Supervised learning is a machine learning approach that's defined by its use of labeled datasets. These datasets are designed to train or supervise algorithms into classifying data or predicting outcomes accurately. So using labeled inputs and outputs, the model can measure its accuracy and learn over time. Supervised learning can be mainly separated into two types of problems: classification and regression. So classification problems use an algorithm to accurately assign test data into specific categories or classes, such as separating apples from oranges, or to classify spam mail in a separate folder from your inbox. Neural networks, linear classifiers, support vector machines are just some of the common types of classification algorithms that we have. On the other hand, we have regression. Regression uses an algorithm to understand the relationship between independent and independent variables. Regression models are helpful for predicting numerical continuous normally values based on different data points, such as sales revenue projections for a given business. Some popular regression algorithms are linear, logistic, polynomial regressions. So the other type of machine learning is unsupervised learning. And unsupervised learning uses machine learning algorithms to analyze and cluster and label data sets. These algorithms discover hidden patterns in the data without the need for human intervention. Hence, they're called unsupervised. Unsupervised learning models are used mainly for three tasks: clustering, association, and dimensionality reduction. Clustering is a data mining technique for grouping unlabeled data sets on their similarities or differences. For example, a really famous one is k-means, a clustering algorithm that assigns similar data points into groups where k is the value representing the size of grouping or the granularity. During this course, we will mainly experiment on these three types, or these three techniques: regression, classification, and clustering, and the other ones can probably be experimented in the future by you guys. So the learning process in the machine learning paradigm is the following. With new input, you make a guess. You try to classify your input data. Then you have to measure your accuracy. You have to measure how good your guess was. And then you just adjust, try to optimize your guess, and then repeat. After that, after many iterations, after many trial and error steps, after learning what the rules are, we now have a model to apply new, fresh data and generate the corresponding inferences. But then, how can we measure how good our guess is, or how good is our model? Let's think about matching X to Y, inputs to outputs. So by estimating the coefficients of a linear equation, in this case, M, the slope, and B, the bias, we make a guess. In this case, we're going to try with Y is equal to 3X minus 1, and we make a guess. So we have our guess here in blue and the desired output in green. If we plot these values, it will look something like this. And here we have in orange the difference between the real value and the estimated value, or my guess. And for each one, we have an error. So the error in this case will be the subtraction between the estimated value and the real one. So if we calculate it for this specific case, we will have -1, 0, 1, 2, 3, 4. So, but at the end, we want to have a score for this particular model, or the current state of the model. So let's try to measure this. So if we take all these values and we want to provide a score, we will actually add all these values. But what's the problem? Here we will have some values that will cancel each other. Some of the errors cancel each other, and that's not something that we want. So what if we square these values and then we calculate the summation? So if we do this, we're going to then remove the problem of the errors canceling each other, and then we have a value. So we scale all the differences: 1 plus 1 plus 4 plus 9 plus 16 is going to be the square root of 31, which is going to be 5.57. So good. Now what? So we're going to adjust the parameters again. We're going to use new coefficients, and we're going to make a new guess. So we try to make another guess. We're going to try now with Y is equal to 2X minus 2. Then we're going to have again the estimated values, the real values, and then we calculate the difference to the power of 2. And we have a new guess, which will generate new errors, a new summation, and a new score. For this specific case, we will have now a value of 2.23, which is actually better because we want to have an error that is as small as possible. Then we keep on repeating this process. We guess, we measure, and we adjust. So we're going to try with new coefficient. In this case, it's going to be Y is equal to 2X minus 1. Then we have the estimated values, the real values. And then in this case, the summation is going to give us a score of 0.0, perfect match. So great. However, normally we are not going to arrive to a 0 error, but we're going to have like different iterations, different epochs, and then we're going to stop at some point. In most cases, we also want to score a measurement of the error that is a little bit more standard in terms of the number of data points we have, because in the previous case, the more numbers the more data points we have, the higher the error in the summation. So we have different metrics. For instance, the root mean square deviation that divides the summation into the number of data points. In this way, we will have, or we will be able to compare different models in terms of error independently of the number of data points. Okay, so this is how we try to give a score to a specific the specific state of a model. But how do we adjust the parameters of the model to reduce the error? So it is basically a trial and error approach, but in an intelligent way. So imagine this is the loss function, which is the function that computes the distance between the current output of the algorithm and the expected output of your system. So let's look at how gradients and derivatives can help us understand how to minimize loss. In other words, how an optimizer function works. In this case, the loss function is a square of something. It's just an example. So it has a parabolic shape like the one you see here. So by adjusting a parameter, we want to arrive to the minimum of the loss function. And the minimum of the loss function is going to be somewhere close to where you see the arrow pointing at its lowest value, whatever it is. So in this case, right there. So when we make our first guess, we calculate the loss of our network based on these initial weights and biases, and we get a value that is sometimes somewhere in the loss curve and sometimes far from the minimum. It's going to be really lucky, but that at your first trial and error step, you're going to get to the minimum. So, but we're going to learn how to get there. So we are somewhere in the loss function, but not at a minimum. So if we calculate the gradient of our value with respect to the loss, it will be a number that has a magnitude. And if it is in zero, the gradient will either be positive or negative, indicating a direction. Actually, the gradient points in the direction that will increase the loss. So in the other direction that you see this orange arrow pointing. So we can flip the signal of the gradient to point in the direction of the decreasing loss. So this direction and magnitude of -1 times the gradient can be illustrated by this orange arrow that you see here, which is actually now pointing in the direction that is going to minimize the loss. So we move in that, so we want to move in that direction, but normally the size of the step that we take in updating the weights is not the full magnitude of the gradient, but the magnitude, the scale, but what we call the learning rate, which is simply a scalar. The step in this case is going to be shown here in gray. So for instance, if the negative of the gradient was 2 and the learning rate was defined by 0.1, then the actual amount to update the weight will be 2 times 0.1, or it's going to be 0.2. So we're going to end up right over there. And then we repeat the process. We get the gradient and the new location of our parameters, and then we multiply it by the gradient by -1, and then multiply it again by the learning rate. Is going to step in that direction, and then we update the weights or the parameters, and we will end up right over there. Then we're going to repeat, and we end up here, and then repeat it again, and we could end up right there when we're getting really close to the minimum. But the problem is that the next step could probably have us overshoot and end up right there. But don't worry. In this case, now the gradient is going to change direction. And if we multiply it by -1, it's going to point now in the opposite direction that was coming before, and still pointing to the minimum of the loss function. So if we follow that step, we might end up here, overshooting again, but the next step might bring us back here, and therefore we might oscillate back and forth, but a good optimizer will drive us towards the minimum of loss. Normally, you can define the number of steps to get there, the number of iterations, the number of epochs. Sometimes you just define that if the error or the loss is not being reduced significantly, then we stop. So choosing the optimal learning rate is really important, because if the value is too large, our steps might have us oscillating over and back too much, like this. With changing values that never reach the minimum, then it's going to take, you have to be really lucky to actually arrive to the minimum of this loss function. But then if we go to the other extreme direction, and we take a really small learning rate, it might take a long time to reach there, a really long time. So of course, this is a matter of expertise, but it's important to understand the goal of the learning rate. And this is what we call the gradient descent algorithm. So if we extend this to 2 parameters, it's going to look something like this. The solution space becomes now more complex, and the gradient descent algorithm needs to go across a surface now, like in this case that you're looking at here. But you're always looking for a single or a global minimal. Normally, you don't. There are not there are cases where you don't have just one minimal, like in this one. So for even more complex scenarios, we might find a local minima, like the one you have over here, which we want to avoid, and a global minima, that is the one that we actually want to arrive. So in those scenarios, the algorithm needs to include an inertial component to be able to leave the local minima while looking for the global minima and not get lost and stuck over here. So now that we understand the process of guessing outputs and measuring the error and adjusting the parameters, let's look into an artificial neural network. So neural networks are inspired by the human brain, mimicking the way that biological neurons signal to one another. So as you can see here, neural networks are comprised of node layers, an input layer here, multiple hidden layers in the middle, and then an output layer. Neurons connect to each other to have an associated weight and threshold for each of the inputs and weights, and then to activate a threshold on the output. If the output of a neuron is above a specific threshold value, the node is considered active and is going to be sending data to the next layer of the network. So there are different types of neural networks. We're not going to get into the details, but you know about the perceptron, the feed-forward neural networks, convolutional networks, recurrent neural networks, and many others. And you have to use a specific one based on the type of application, the type of data, the input data that you have. So let's talk now about just neurons. A neuron's output is a function of its inputs. In this case, we're going to have just one input, X, and the output is going to be Y. And there are only 2 parameters to adjust: the weight for each input and a bias. In this case, we have just one input, so we have just one weight and one bias. A single neuron can help us implement a really simple first scenario called a linear regression on just one input and one output. So probably over these days, you're going to go through these examples. This is just a really common example that you can actually use on Google Colab. And here we're just going to run this really simple example on one neuron, trying to optimize the weights and bias to match X and Y's. So here we establish the structure of the neural network. We're going to use, of course, TensorFlow and Keras libraries. We just define here the structure of the neural network with one layer and just one neuron. We use a stochastic gradient descent for the optimization of the parameters and the mean square error to measure the error. We declare the inputs and the desired outputs, and you're going to see here that are exactly the same ones that we used before on our examples on how to modify the parameters and try to arrive to a solution. And then we just train the model. After running the algorithm, after running for many iterations, in this case, you have 500 epochs in this case, we should arrive to a pretty decent model. If we test the model, then in this case, we're going to test the model for input 10, and it's going to give us an output is 18.98, which is really close to 19. If we test for the whole training data, in this case, it's going to be that we defined at the beginning, it was -1, 0, 1, 2, 3, 4. The outputs are going to be -298, -0.99, 1.0005, and so on, which is actually really close to -3, -1, 1, 3, 5, and 7. We could actually check for the final coefficients of the model, and you see here that is 1.9975 and -0.9922. So the model's output for the test inputs are close but not perfect, because the parameters are also close but not exactly 2 and -1, which were the values that provided 0 error in the past. It was, now the equation is y is equal to 1.9975 x minus 0.9922, which is close, not perfect, but probably good enough for most cases. So we arrived to this model for one neuron. It's a very simple model, but now what? So we have this one, it has been trained. So how we implement more complex scenarios? So let's think now about classification. In the previous scenario, we had just one input and one output. What is going to be the case if we require multiple inputs? So let's think about this one. Then we need to consider more neurons to take care of the different inputs. So here for 2 inputs, we have one input layer with 2 neurons and an output layer with 1 neuron. And we can use this input layer to scale the inputs and the output layer to weight the inputs to calculate the output. So what about more inputs? So let's consider the classification problem of taking pictures of dogs and cats and trying to identify if we have a dog or a cat in the picture. In this scenario, we have 2 classes. Then we're going to have 2 neurons in the output layer. And we're going to have one that is going to be active for cats and the other one that is going to be activated when there's a dog in the picture. So what you want is when there's a cat in the picture for this neuron to be active and the other one to be, or to have a really low output, a low value on the output, and then the other way around when there's a dog in the picture. So what we need is the label input to properly be labeled to what you want to be to the neuron that you want to be active on the output. So you have data, you have to take different pictures. In this one, a picture of a cat, and then the label is going to be 1, 0. This one is going to be, this is coding the neuron that you want to be active, and when there is a dog, that you want to have this label assigned to this picture. And of course, we can extend this example to many different other domains. But you know, when you start working on machine learning, specifically with images, it's difficult to try to understand how the input is going to be a map to the structure of the neural network. So let's think about a more technical example. So let's consider the MNIST database, which is a large database of handwritten digits that is commonly used for training various image processing systems. So for each image, we need a proper label for the training algorithm. So in this one, when you have an image with a 0, like the one that you see over here, then the label is going to be 1, 0, 0, 0, 0, meaning that this is the first class that we want to classify. So for 1 is going to be this neuron, the specific neuron for 1 that you want to be activated when you have this input, or any of these kind of ones, and then the same thing for 2, and so on for the other ones. So this database has 60,000 label training examples and 10,000 label validation example, and it is really easy to code this with TensorFlow and the Keras libraries. So what we have is a set of 28 by 28 grayscale images. So each of these images are just 28 by 28 pixels, and you can see here a 7. Each, of course, with its corresponding label, which implies that we're going to have 784 neurons at the input layer, 1 neuron assigned to each pixel in the picture. So 28 by 28 is going to give us 784 pixels. And of course, we're going to have at least an additional layer, that is the output layer, with 10 neurons, 1 per digit, or 1 per class. So just stop here to think how many different parameters we will have to adjust for this neural network to be trained. So we have 784 weights and biases for each of the neurons at the input layer. So we have one weight and one bias for each of these ones. So we have 784 weights and 784 biases. And then for the second layer, the output layer, we have 784 weights because this is fully connected to the previous one for each of these neurons. So it's going to be giving us 7,840 in total and 10 biases for the outputs. So we'll have more than 8,500 parameters to tune for such a network. So in the past, it looked easy when you have a linear regression, but this is way more complex. And this is where the optimizers and the learning algorithms are being tuned to do it properly and to do it as fast as possible. So this is something that you cannot do by hand. So again, you could run this example in Google Colab using TensorFlow and the Keras libraries. We won't go here into the details, but you have to load the data set, the MNIST. You normalize the data to have it between 0 and 1 because these are grayscale that are between 0 and 255. Then you structure the neural network that you want. So you have the inputs with 784 neurons. You have a hidden layer with 20 neurons and an output layer with 10 neurons, one per class. We define here the optimizer, and we define 20 epochs, so just 20 iterations to train the neural network. Sometimes you use a fixed number of epochs, like in this case, but another approach, as I was mentioning before, could consider the difference of the error between epochs. And if this difference is below a certain parameter called epsilon, we could consider that the error won't reduce much more and stop there. Normally, having a large epsilon could imply learning divergence, and a small epsilon could imply a small convergence. So by using, by evaluating your system, in this case, we have a set, a training set and a validation set. So the accuracy for the validation set will be normally slightly lower as the model hasn't previously seen this data and may not be fully generalized for all data. You can also classify particular images in this case, for example, to compare to the actual label. So in this case, the accuracy was 86%. And then if you classify the first image here, this is what we're trying to do here, the first image, and the first image was a number 9, and then you see which neuron has the largest value on its output, and this one is over here, which corresponds to number 9. And that's what we actually want. So again, remember, we are looking for different parameters, weights and biases, thousands of them in a multidimensional solution space. So this image, or this is something that you can look on YouTube videos on different courses on neural networks. This is just a representation of such a search process in the solution space, but actually plotting it will be impossible because of its dimensionality. So it will be almost impossible to plot this actually loss function with all the different parameters that we are actually tuning and moving. These images are part of, in a couple of slides, I will show you the link. I think it's a really short course on YouTube, which is really interesting, and for people who are starting with neural networks, I think is really useful. So a more complex and probably more realistic implementation of such a system will include more hidden layers like the ones you see here. We have, again, the 784 neurons on the input layer, 2 hidden layers, and 10 neurons on the output layer. So if you want to analyze this in a logical way, if you can, in terms of what humans think it's logical, since we're talking about linear combinations of inner characteristics of the input data, common sense will make you guess or think that the first layer oversees recognizing segments of the handwritten digit, for example, short segments, short lines, curves, like the ones you see here on the different colors. So you think that this first hidden layer is going to take care of identifying those small lines. And then you will expect the second layer will take these segments and construct more complex shapes like long lines, circles, ovals, like the one you see here, like the one like this oval in yellow, or this curved line in kind of pink or red. And then the last layer will just combine these two. For example, if you're saying that this neuron is kind of creating this oval and this other one is creating this shape here, then the neuron that is looking for the 9 will actually look for these two and combine it and then be activated for 9. That's probably what you think is logical in this structure. However, this is what the second layer of neurons actually look. These are the biases for the second layer of just one single neuron. So can you identify any clear pattern over there? At least I can't. So the only thing that we know is that the network is trained and does a good job classifying the input digits, but normally we just don't exactly know. For some other cases, for example, for image processing, it's typical to have convolutional networks that have some kind of mask to help the network look into certain areas of the image. But if you just train the data, you just cannot, ideally, you cannot control how the weights are going to be changing, but you just know that the network does a good job. However, in some cases, even though there's not this clear structure, in some cases we just see data that is complete noise, and we have a really strong output on the neural network. So it learns in some way, but of course it can also make stupid mistakes like this one that is, for any human, is very clear that that's not a number 5. So for the interested reader or watcher, I suggest looking at a set of videos about neural networks by Grant Sanderson. It's just really short videos that you can see over here if you want to scan it on this QR code. And he has a 3 blue, 1 brown project on YouTube. Just check it. What probably we have seen really fast here is the first 3 chapters, which is what is a neural network, how gradient descent works, and what is backpropagation. That is a way to train the neural network. Probably the last one can be optional because it's actually the calculus on backpropagation. Okay. So of course, there are going to be many different issues, as it always happens in engineering, in computer science. When you fix something, something else is destroyed or is not working properly. So not everything is perfect, and there are some issues. So let's first take a look at how data should be split during the training process. If we take the whole data for training the model, the network has no context to measure how well it would perform with data that has not seen before. Hence, the network, you have to split your data into data for training. The network sees a subset of data to train and uses the rest of unseen data to measure its performance. Moreover, you would like to have then, you can use a subset of data to train, another subset of data to measure its accuracy during the training process, which is what we call validation, and finally, another subset to measure its accuracy after it has finished training the test data. So if you measure the accuracy on these 3 data sets, it's going to be different. It is normal to be different. So with this in mind, it's completely normal to have a reduction in the accuracy of the model depending on the data we use to measure. So normally on the training data, you have a really good accuracy. In this case, for example, 0.999, because it's the data that you're looking at. So if you're learning with something, it's like when you're studying for an exam, and if you do again the same exercise, mathematical example, of course you're going to do it right, and that's why you have a large accuracy. But when they give you an additional exercise that is not exactly the same one that you did before, probably you're going to have a lower accuracy. And of course, with test data is normally what we have when we have a deployment. You can have even a lower accuracy. Test data is normally the most difficult one because if you haven't prepared a good data set for training and validation that is general enough or that captures the different conditions of a real deployment, then it's going to be really different, the results of the accuracy on the data set for training, for the validation, when compared when you deploy the system. So at the end, the real accuracy is measured against test data that's coming from a real deployment. And at the end, you actually don't, of course, you're training the system aiming to increase these values, but the one that you actually want at the end to be really high is the test data. That's the one that you're going to be using on the real deployment. It doesn't matter the other ones. So of course, we would like to have a very accurate result in all three data sets, implying that the results achieved during training will replicate well in a real deployment, but that's not necessarily the case. So this is one of the most difficult problems that we have, that is model fitting. So in the context of machine learning, model fitting refers to the accuracy of the model's underlying function as it attempts to analyze data with which it is not familiar. Underfitting and overfitting are common problems that degrade the quality of the model, as the model fits either not well enough or too well. So this causes the model to make predictions either too closely aligned or too loosely aligned with its training data. So what you want, for example, in these points over here, is to kind of like the model to learn the trend of the values. In this one, probably you will have a very good prediction during the training process, but it's completely overfitting. It's probably not going to generalize well under real deployment. So an overfit model predicts training data too well because it has learned the data details, but also the noise. You see here that probably even though you have here a trend, you have noise. Overfitting the model is kind of like learning the data, but also the noise too well. An underfit model is not accurate as it neither accurately analyzes its training data nor the data that has not been seen. So one last simple example. Considering model A, there's a common misconception that if the test accuracy or unseen data is lower than training accuracy is because the model is overfitting. So let's look at this one. Model A has a really good train accuracy, but of course it has a test accuracy that is lower than the train accuracy. However, the test accuracy should always or almost always be less than the train accuracy, and the distinction between overfit versus appropriately fit comes down to how much less accurate it is. So when comparing A and B, for example, in this case, model A is a better model because it has a higher test accuracy than one that you see over here. It has a higher test accuracy, and although the test accuracy, although the test accuracy is slightly lower than 95, it is not significant different. It is not a significant difference that suggests overfitting is present. I mean, of course, it's lower, but it's not really low. And you wouldn't choose model B, even though the train accuracy and the test accuracy is almost exactly the same, just because of that factor, but you just want to check or compare the different models just based on the test accuracy or the accuracy on data that's coming from the real deployment. Model C is a clear case of overfitting. As the train accuracy is really high, we see here 99.9%, but whenever we deploy this model into a real scenario, we have the accuracy decrease by a lot. You have 45% here. This is kind of like tossing a coin that this model does not work. Of course, this distinction is subjective, but comes from knowledge of your problem and data and what magnitudes of error are acceptable. For some cases, 87% is acceptable, for others not, and you will have to aim for something like 95%. And that's going to, of course, depend on your system. So I would like to thank, I mean, all this material, part of the material has been built by myself, but most of them, most of the material that I use as an input for this comes from Sean Hyman from Impulse, Pete and Lawrence from Google, Professor Vijay and Brian from Harvard and Columbia, from Marcelo and Unife. So I would like to thank all this TinyML education community for all this material, and thank you very much for attending. I just hope, again, I was running through this material. I just wanted to give you the main concept really briefly, but I just want you to be inspired, and I hope you fall in love with this topic and to follow the rest of the workshop in this week. Thank you, Marco. I guess I see a lot of comments. I hope there are questions.
Thank you very much, Diego.
Thank you.
Clapping my hands on behalf of the party. That was great. I mean, great challenge, right? To concentrate all this material in 1 hour, and very positive comment. So we have, I guess, 10 more minutes before the next talk. So maybe if you want to take some of the questions, or
maybe, maybe for example, the last one here. For example, for Matheus, is accuracy? Oh no, sorry, I think from here. What is the case when test accuracy is higher than the train accuracy? Is possible, Diego, something like?
I'll be just really lucky, I will say. I mean, it's probably you can just have like a good shot and good luck and just have a larger test accuracy, but I will say it's normally not the case. It's normally not the case. It's not common. Yeah.
Maybe one comment, when I saw, but not with the test, I saw sometimes the first time that I saw the validation result when you do the training higher than the training is because you drop out. Because during the test you use dropout. Sometimes you can have validation higher than the train, but usually train is the highest, validation the middle, and test in the lower. I say my experience.
I mean, I would like to say, I mean, in this process is the key component is how you collect data. I mean, how good you collect data. I mean, you need to understand your problem. You need to understand where it's going to be deployed, and try to collect data that characterizes all the different scenarios of how it's going to operate the system. If you collect good data, normally it's going to be the case that the training and the validation is going to be close to the test data. If you're not doing a good job, and which is normally a case with when you're starting with this, you just collect some data and you start training, and then when you deploy, it's just a mess. But if you do a good job, collecting data is a key component so that you don't waste your time in the future retraining the system over and over again until you just achieve a good test accuracy. Just many different messages. I am like an hour before.
The previous one, I think that I tried to help with some. The last ones I didn't answer. If you go to the end, maybe it's better.
Let me check. Someone asked about probably what's the best percentage deviation between test accuracy and validation accuracy. Again, I guess it's just going to depend on what values of error is acceptable for your system. I mean, I can tell you probably it can be acceptable to have 5% difference between the test and the and the validation accuracy, but for some other cases, it's not going to be acceptable because if it comes from 90 to 85, and if 85 is not good for your application, then it's still bad, even though probably the difference is not big and really that big. So it's going to depend that this is application specific. So for Agustina is asking about the difference between validation and production data, or probably just test data. I mean, normally you just, and you're going to see this, probably many of these questions are going to be solved during the rest of the week. But for example, in the example that you're going to see the rest of the week, you're going to collect data with your phones, with the TinyML Arduino kit. And this is going to be your training and your validation data set. But for example, if you're going to probably you're going to do the keyword spotting example, and you're going to start saying words to the microphone, and depending on how you do it, how well you do it, then when you test it with new data, I mean, you use this to train and validate during the training process, but then you just deploy the trained model to the Arduino processor, which is a Cortex M4, you just deploy, and then you just start taking data from the microphone online and then classifying it online. That's kind of like the production or the deployment of the system. But if you didn't reproduce well the conditions where this model is being actually deployed, then you're not going to have a good accuracy. For example, if I collect the data here in my office where I have no noise, and then I deploy it and I use it outside where a lot of noise, then it's going to be probably not good enough. So probably that's kind of like the difference between the validation, the one that you use during the training of the system, and then the production or the deployment of the system.
There's a few questions about overfitting and imbalanced data sets. Maybe you can comment on that.
Okay, so overfit, I mean, as I said before, probably you have many different parameters on this neural network, so different models in machine learning. If you train it by a couple of epochs, it's going to give you some values, and probably if you keep on training it, and if you include a even more complex machine learning model with many hidden layers and many other and with many neurons per layer, you probably are going to learn like all the values of the inputs and also the noise. So the problem is that it's like if you are studying for an exam and you just learn the answer, you just learn the answers, but you don't know how to get from the question to the answer. So if they ask you exactly the same question, you're going to make it right. But if they just change a little bit of the question, you're going to make it terrible, because you just learn exactly all the input data, the information, but also the noise. Okay. So if the noise changes, then you're going to make a bad job classifying new data with different noise, for if I can say something. So that's kind of like overfitting, just learning everything. You have to have general, you just need to be able, for the model need to be able to learn the characteristics of the information, not the noise, just the patterns, the features of the information, not the noise. For example, if you want to understand a pitch of a sound, then you just want to learn the basic frequency, but not just specifically all the shapes of the signal. And the other one was what? Unbiased. Yeah, imbalanced. So the problem is that when you're going to train this model specifically for classification, it is good that you have enough information and enough data for all the classes. So if you're going to have, again, the keyword spotting problem, that you want to say yes and no, and you want the system to identify when you say yes or you say no, but you want to have enough data for both of them, so that the system can have enough information from all the classes to perform well during the deployment. So imbalance is probably that you have, like, from your data, you have 70% that it's the information from the yes sound, and just 30% for the no sound. So you have you want, again, that's kind of like what I was saying at the beginning. You want to have enough information from all the conditions of the system, so that when you train, the system can learn the features of each of these classes and perform well during the deployment. I don't know if Marcelo wants to. Marcelo is the expert here on real deployments on these systems. I'm trying to learn on the other ones.
Now, there's one question, very interesting one from Dipesh about doing
sensors.
Yeah, doing the training with one sensor and then using another sensor for the deployment.
That's difficult. I mean, because it's going to depend on the accuracy, on the sensitivity, on the range of the sensor. So, I mean, I guess you can use different type of sensors as long as you keep the range of the sensor, the sensitivity, the way it operates, kind of like its linearity. For example, if you have a linear sensor and the other one is not linear, it's not going to give you the same information. But I'm guessing if you have different kind of sensor, but both are digital, that after some point you have the same values, can work the same way. But it is a problem. It is a problem having different kind of sensors.
So Diego, I mean, thanks a lot for the presentation, for the explanation, for the answers. I think we need to wrap up and move to the next speaker. So again, thank you so much. I hope you.
Thank you, Marco, for the invitation.
You will be on Discord. I know you're active on Discord, so if you have more questions for Diego, he can reply on Discord. I have seen some other questions about the slides and the video. Yes, as we wrote in the chat already several times, the videos and the slides will be available on the website. Give us, the time to download them from the Zoom cloud. So that usually takes 24 hours. So once they are available, we will post them on the workshop webpage. Okay, so don't worry, they will be there.